All right, let's go ahead and look at some of the information necessary to work on the module folder 5A, Pre-Lab Relativity. Now, this one's a little bit different in that I don't have an exact simulation or not the same type of simulation that we've looked at before. Here is a website where they've built up sort of a different kind of cartoon for us, but it does still work. Unfortunately, there's a bunch of ads and things around it, so don't click on any of those. Um, but at least we can run the simulation and see what's going on. Okay, so if we set the spaceship speed to 0 times the speed of light, and think about it, that means nobody's moving, right? It's just sitting here. And when we run the simulation, we want to see what's going to happen. So what we're looking for here, we're ultimately are trying to test is time dilation. So time moves differently for a moving source compared to whoever is watching that source that's moving. Okay, so well, we're not going to make it move this time. It's going 0 times the speed of light. And let's see what happens. So inside here is 1.000 seconds, 1.000 seconds on the outside, so nothing changed. If something moves sufficiently slow, um, so even if it technically is moving, but it's moving lot less than the speed of light, then there's not going to be any discernible effect. Think about plus or minus some rounding error. Um, you're just not going to be able to detect anything. Okay, but this we actually set to 0 and said it's not moving at all. So let's read the question. Determine the elapsed time for the person inside of the spaceship. Look, it says here we had the clock go around 1 second. It's kind of a weird clock, but we're not going to talk about that right now. Okay, then question 2. Same thing, 0 times the speed of light, run. Well, we already did that. To determine the elapsed time for the person outside the spaceship. Okay, so outside the spaceship is also 1. So there we go. Okay, now relativistic factor, sometimes also called the Lorentz factor or a gamma factor. There's a complicated formula for how you calculate it directly, but the nice thing about this simulation is it allows us to do it without the original formula. We sort of twist things around and see. As it turns out, if we use the ratio of those times, if we happen to know both of the times, then we can work backwards and we can figure out what that factor was. Well, if both of the times are 1 and we stick 1 and another 1 inside of a fraction, then I think predictably you would think that we would get 1. Okay, so nothing super tricky going on the first few. But as we start to pick up speed a little bit, we're going to see things change for questions 4 and 5. So we'll try to leave the scale here where it's zoomed where we can see both of these at the same time. But we want to go at 0.15 times the speed of light. We're going to run the simulation. We're going to see how time is different. All right, so now, there we go. So, oh, that's different this time. Look. So inside the spaceship is 1.000 still. So that's our reference point. We'll call this 1 second always. But outside, somebody watching the spaceship, because it's moving very quickly, they're actually going to see time as a little bit different number. And so notice here that it's a slightly larger number. Okay, so let's read the question. Let's see which one of these we're trying to look for now. We want first the person inside the spaceship. All right, well, look, inside, clock runs normally as far as we can tell. It's 1 second that has passed. Okay, and then we notice from here, again, look at outside, that's not quite straight down. That's a little bit further around, so there's a tiny extra little bit here that's passed. So 1.011. Okay, and like I said earlier, the ratio of these, if we set them in a fraction, will help us see the Lorentz factor, the gamma factor, or the relativistic factor, different names for the same thing. So if we stack this on top of just the number 1, then we get that number back again. Okay, so how did the time change for the person inside the spaceship? So they saw 1 second earlier, they saw 1 second again, then it's the same. Okay, but for the person outside the spaceship, they saw 1 second, then they saw 1 second plus a little bit, So time got a little longer. So dilation, dilate means to stretch or to get bigger, right? So time dilated, and so we saw a bigger amount of time. Okay, then find the minimum spaceship speed necessary for a relativistic factor to be at least 1.5. So remember, we could stack these times and make a relativistic factor out of that. So basically, I just want to make sure that this yellow number comes out to be more than 1.5. So looking at our answer choices, we can't go faster than the speed of light. If I tried, I can only get to 0.99, right? So 1.5 is obviously not going to do it. Then let's try one of these other ones. So let's try a half. So 0.5, half the speed of light. We want this yellow number to turn out to be 1.5. No. Bigger, but we didn't quite get there. All right, so next answer choice, 0.75. So 3/4 of the speed of light. Maybe. There we go. Come on, 1.5. Yes. So just a little bit over 1.512. So, for small restrictions on what we can dial the speeds into, that's as close as we're going to be able to get. So a little less than 3/4 of the speed of light will make somebody have a relativistic factor of about 1.5. So where was that? That's this one, right? So 0.75 was as close as we could get. Okay, so now if I want to go at least 2, well, we can't go 2 times the speed of light. It's not possible to go exactly the speed of light. We can't go more. And we already tried this one. That was the answer to before, so it seems like it's going to have to be here. The only number left that's bigger. So let's try 0.87 and let it run. And it seems to have worked. So plus or minus a tiny bit. Again, we can't dial in perfectly what these values need to be, but that got us reasonably close. It was also the only choice left that really made sense. All right, and that's it.